The plasma and the form element.
A lot of things. What are those things with plasma, right? Blood really is plasma and what else?
Formed
And the
elements.
formed elements. So we've gotten this far, right? And in general, what is plasma, or what does it do? Okay, it's non-living. It's not actually cells. Okay, it's really like 95% water. And in that water, we have all these different things. It's carrying hormones, it's carrying oxygen, it's carrying carbon dioxide, it's carrying waste, it's carrying nutrients, all this stuff. So really, plasma is just that. It's sort of the carrier, it's the matrix, the medium in which all this stuff is flowing through. Nutrients, blah, blah, blah.
What is that word next to 95%?
Water. Sorry. If you ever need me to, I'll just do it in all caps from now on. Use waste, oxygen, carbon dioxide, hormones. Okay, so that's good. Plasma is fairly easy. Where it gets a little bit more detailed is the formed elements. So we talked about 3 different formed elements. What are these 3 formed elements?
Erythrocytes, leukocytes.
Thrombocytes.
Erythrocytes, leukocytes. Okay, so in general, what do each of these 3 things do? Just very basic.
Carries respiratory
Let's start with
gases.
erythrocytes.
Carries respiratory gases.
Carries, yes, carries gases, like oxygen. Leukocytes, what do they do?
Fight infections.
Fight invaders or infections or immune system, right? Immunity. And then thrombocytes,
Help with blood loss.
right? This hemostasis process. Okay, so this is good, and this is a great foundation. And really, when you're teaching this to yourself, you're going to want to tell a story. Okay, if you know what the formed elements are, all these different parts of the body, then you know generally what it does. You can really start to tell each of their stories, right? So we'll start with erythrocytes. Erythrocytes, like we said, carry oxygen. Okay, and that's good to know. But how do they do that?
The oxygen binds to the cell.
Exactly. Okay, and so remember when we're talking about function or physiology of anything, we can always relate it back to the anatomy. So let's talk a little bit of erythrocytes' anatomy that makes them so good at carrying oxygen. Okay, erythrocytes, what are they really? Yeah. Okay.
2 beta chains and 2 alpha.
But what do they look like? Concave. Yeah, they're little concave guys. Look sort of like donuts or inner tubes or whatever. They have a large surface area compared to their volume, which is great for gas exchange. Okay, large surface area to volume ratio. This is going to allow gases to enter the red blood cell because you have this large area, this large surface area, which can interact with the world around it. Okay, this is good. What else about erythrocytes make them good at carrying oxygen? If I look inside an erythrocyte,
They don't have a nucleus.
no nucleus, right? No nucleus. And why don't they have a nucleus?
They want to leave space for more oxygen.
Yeah, no nucleus. Lots of, and what's carrying the oxygen?
Iron.
Which is part of the hemoglobin molecule. 97% of the proteins in a red blood cell is hemoglobin. There's no nucleus because we've ejected the nucleus to make room for more hemoglobin. We just have all this hemoglobin packed into this little sack of hemoglobin, really. this is what makes them so good at carrying oxygen, is because there's a large surface area to volume ratio, there's no nucleus, and just packed with hemoglobin. Okay, perfect for carrying oxygen. And so we've talked about hemoglobin a little bit. Maybe we'll go into a little bit of detail about hemoglobin now. Right? What is hemoglobin made up of?
Globin protein.
Okay. So you have these 4 globular proteins, and there's 2 alpha, 2 beta, and each of those contains a heme group. And each of those heme groups contain an iron molecule. And the iron is really what's binding to the oxygen. Okay, so every hemoglobin molecule, which is making up 97% of the proteins in this red blood cell, can carry 4 molecules of oxygen. Why? Because you have 4 proteins, each with a heme, and each heme with an iron. Okay. So that's good. Continuing on with our story, why carry oxygen? Why do we need oxygen?
The tissues.
Right, we need to get it to the tissues. So in order to drop it off at the tissues, of course, oxygen is binding reversibly to hemoglobin. So why not just have as much red blood cells as you possibly can have?
Because it'd be blood clot.
Your viscosity will decrease.
Because of the viscosity, right? So here we're going to talk about the hematocrit viscosity relationship. Okay, so again, you know the anatomy of a red blood cell. You know it's really good at carrying oxygen, and our cells need oxygen. So why not just have a bunch of red blood cells, right? Well, because of this thing here, right? Viscosity, right? The more red blood cells we have, or the higher our hematocrit, the higher our viscosity. And viscosity is really what? Right, a measure of thickness. So here we have our first problem, really. We want oxygen. We need oxygen, actually. We don't just want it. But our blood can't be too viscous, right? So we have to have sort of a balance between viscosity and hematocrit, ultimately our oxygen carrying capacity. This is why we talk about these things. So how do we balance these things? Where do red blood cells come from? And why are they being made?
The bone marrow.
Okay, so this is part of,
Well, wouldn't the body destroy some of its
what's that?
wouldn't the body destroy some of its I'm thinking calcium reduction, forget it.
Okay. We'll talk about the destruction of erythrocytes in just a second. But right now we want to talk about the production of erythrocytes, right? What is the production of erythrocytes known as? Poiesis. Okay, so again, erythro means red, and then cytes are cells. Erythro here, again, red, poiesis meaning making. So erythropoiesis is the making of red, or the making of red blood cells. Okay, so we know that starts in the red bone marrow. And, well, I guess we might as well talk about the process of erythropoiesis first. Where do all red blood cells come from? What cell do they start out as?
Bone marrow?
Stem cell.
A stem cell. This stem cell is hemocytoblast. And as we move from this stem cell to a specialized red blood cell, there's a 3-step process. What happens?
Releases erythropoietin.
The first thing okay, so again, think back to the anatomy. What is a red blood cell? Really just a sac of hemoglobin. So how are we going to go from this stem cell, which is not a sac of hemoglobin, to a sac of hemoglobin?
Prourethra.
What's the first step?
Is this the
It
negative feedback
decides.
you're referring to?
Not yet.
Okay.
So, exactly. The first step is we're going to, so from going from a regular cell to a sac of hemoglobin, we have to make a bunch of hemoglobin. Hemoglobin, like you said, is made up of proteins. In order to make proteins, we need a bunch of ribosomes. So the first step will be ribosome synthesis. The second step then. Exactly. Right. And again, you're looking at your notes, and that's okay, right? I don't expect you to have mastered this material yet, but this whole process, this trying to teach it to yourself or trying to teach it to someone else, is going to show you where you need help, right? If you don't remember the steps in erythropoiesis, then just go back and look at it, review it, then try and teach it to someone again.
What's that second word? I'm sorry.
So the first step is ribosome synthesis. We make all these ribosomes, which again are like the factory workers of the cell. They make proteins. The second step is we're going to use those ribosomes to crank out hemoglobin. All right, so the second step is hemoglobin accumulation. And then the third step, we have so much hemoglobin, we want to make room for even more hemoglobin.
You eject the nucleus.
All right, ejection of the nucleus. After all three of these steps, we're basically an erythrocyte now. So this is the process of erythropoiesis, and again, this is happening in the bone marrow. But back to this problem, right? We know how we make red blood cells, or how they change from stem cells to red blood cells. But what's stimulating this process, and why is it stimulating this process?
Erythropoietin.
Okay, erythropoietin, I like that answer. Where's erythropoietin coming from? From the kidneys, right? So, and why would the kidneys release erythropoietin? Blood volume, not necessarily.
The amount of RBC in the hematocrit.
Yeah, this thing right here, your kidneys are basically sensing hematocrit. Okay, they can tell when your oxygen carrying capacity is too low. Okay, so O2 low is going to stimulate the kidneys to release erythropoietin. Erythropoietin is going to travel to the bone marrow where it stimulates the production of red blood cells. And then what's my response to low oxygen?
Increased oxygen.
Now I increase my red blood cells. Increase O2 carrying capacity. And we have our first negative feedback loop that we talked about in class, right? The stimulus is low oxygen carrying capacity. The response is increasing that oxygen carrying capacity. It's super important that you know erythropoiesis is controlled in this way. When we have low hematocrit, our kidneys will tell our bone marrow to produce more red blood cells to bring our hematocrit back up, and therefore bring the ability to carry oxygen back up. Okay, so I definitely want to think about it in this way. That's great. We talked about how red blood cells are being produced. Now let's finish this story with how red blood cells are broken down, right? So how are red blood cells broken down?
Heme and globin are separated.
Well, again, what are red blood cells? Really sacs of hemoglobin. So what we're talking about
Hemoglobin.
with RBC destruction. Hemoglobin is broken down into heme and globin. What do we do with the heme? What do we do with the globin?
Heme is turned into bilirubin.
Okay, so part of it is released in bile as bilirubin. And then what about the iron molecule we have there?
It gets saved.
Yeah, we're gonna reuse, salvage iron. What about the globin, this protein?
It's metabolized into amino acids.
broken down into amino acids, and then of course those can be reused. Is there anything I didn't cover with erythrocytes that you want to cover? Again, when you start to tell the story, you can go through all these things that maybe you just thought of as flashcards before and realize they're all interconnected, right? The anatomy, the physiology, and how we regulate all these different processes.
What is A?
Amino acids. All right, so we'll move on. The next formed element we talked about are leukocytes. Bilirubin is the bile, really. And then the iron, which is salvage for reuse, iron here. Okay, so let's talk about leukocytes now. I guess I can leave that up for a second. This time, leukocytes means what?
White blood cells.
White cells, right? So these are my white blood cells. And we talked about how they're the immune.
Couple of us have a question. Under amino acids, where is that part?
Oh, reused.
Okay.
Yeah, sorry.
I read glasses,
I see
so
it.
it's hard for me to read those words.
Yeah, no, my handwriting is awful. Not just for glasses.
And drawing is nice.
He's good at drawing.
I don't know. I'll work on it. Try to use all capital letters. Okay, so leukocytes. We talked about how they're the immune fighting arm. How do they do this?
Don't they like call it enzyme? Or they engulf it, phagocyte, and the phagocyte like eat the invader?
So we have different ways of fighting these invaders, depending on the invader sometimes. Really, it boils down to we have different leukocytes that do different things, right? So instead of just talking about one erythrocyte and what it does, we have different leukocytes here that we want to focus on. And we can break these leukocytes into two groups.
Granules and agranules.
Granulocyte and agranulocyte. Right, the big difference is what?
The granules.
Right, the granulocytes are filled with granules, so that's why I like to call them, well, they end in fill, right? So these are your neutrophils, your basophil, and your eosinophils. And in general, you want to know a little bit about each. Neutrophils do what, really?
Engulf
They're
bacteria.
first responders and they're phagocytic. What about basophils?
Release the histamine.
They have histamine, which is inflammatory chemical. And then eosinophils. They don't engulf worms. Usually these,
They form around them and then they break down the parasite.
yeah, so in order to do that, they release their granules, which are lysosome-like granules, into the extracellular fluid. They sort of form around this big invader that can't be swallowed by a cell, right? This big parasitic worm, and throws acid on it, basically, like stomach acid. You know, we put food in our stomachs and then break it down. Flies, everybody sort of flies, you know, eject their stomach acid onto their food. This is sort of like a fly, right? Lysosome-like. Eject whatever. Okay, okay, I promise you, there's going to be questions on your exams where you're identifying, you know, which leukocyte is the one that releases histamine, or which leukocyte is the one that is the phagocytic first responder. Okay, so you want to be able to know a little bit about each. Maybe not too much in detail, but at least these things that we got written on the board. Okay, so for agranulocytes, we have two types here. What are the two types of these?
Monocytes.
Monocyte and lymphocyte. Now lymphocytes are special. We actually have two types of lymphocytes. Does anybody know the two types?
T cell and B cell.
T cell and B cell, and they each have their own sort of job. T cells are going to do what?
Attack. They attack the viruses.
Okay, so they attack invaders found where? Inside the cells. Okay, these are cellular immunity. Okay, think about this for a second. All of these things are going to eat or release or destroy things that are outside of cells. How would you kill something if it got into your cell, like a virus or some other parasitic bacteria that enters the cell, right? This is the job of the T cells. They're very, very important because they can go around and touch each of your body cells and determine whether that cell is sick or not, and then tell that cell to kill itself, basically. Not joking. So T cells are your cellular immunity. They're going to kill things found inside cells, like viruses.
Right there where it says erect T cell,
Yeah.
that's cellular what?
Cellular immunity.
Immunity?
Yes. And then B cells are what immunity? They release antibodies where? In the plasma, in the fluids, right? So this is known as your humoral immunity. Okay, and then monocytes, what's cool about them?
They
Yeah, they're sort of like neutrophils in a way, except for they're larger and more robust, meaning that they don't just go in, first responder, and attack and then die. These guys stick around and continuously eat things, and then they present those things to lymphocytes. They actually activate lymphocytes, and we'll talk about this in the immune system chapter. But I'll just put robust phagocytes. You should also know how monocytes enter, or neutrophils enter the tissues, right? These things are floating around in the blood. We know they're formed elements, but we don't always have infections in the blood, and in fact, we wouldn't want an infection to get to our blood. So these guys need to leave the bloodstream, enter the tissues, and attack the infection there, right? Wherever the site of infection might be. Okay, so how does that happen? Does anybody remember that?
They're attracted to like become involved in release of the infection.
Okay, exactly, right. Histamine. Oh, eosinophil. Lysosome-like granules.
The robust, you're talking about robust viruses.
Oh, robust. This? Lysosome-like granules. So neutrophils, when they leave, neutrophils and monocytes, they leave the bloodstream and actually enter the tissues. They do this in a two-step way. Did we talk about this? Let me just triple check, because
I don't think so.
I know we talk about some immune things here, but sometimes I get confused.
Yeah, boy.
I'm not seeing it in the review, therefore I'm afraid it's not here. And it most certainly isn't. Okay, forget that. This is part of the immune system chapter, which we'll go over. So forget that. This is good enough for now. Good. So, just like we talked about production of erythrocytes, we should also talk about production of leukocytes. Now, leukocytes are full cells, right? They live much longer than red blood cells because they have a nucleus, and so they can repair themselves. We don't necessarily continuously monitor levels of leukocytes in the blood like we do red blood cells, right? We don't need to because they live a bit longer. Instead, what is your main stimulus for production of leukocytes?
Nucleopoietin.
Infection?
Other red
Some
white
sort
blood
of
cells?
infection, right? If you have a bacterial infection or a viral infection or whatever it is, if you have a foreign invader enter your body, this is going to stimulate more production of white blood cells, and that makes sense. What do? They fight invaders. So if an invader happens to come in, we're going to make more of them. Okay. So leukophoresis. Stimulated by, an infection. Okay. It's actually the white blood cells which ask the bone marrow for more white blood cells. Right? They do this by releasing interleukins.
Say that again?
Upon contact with an invader, the white blood cells will release interleukins, or between white hormone. Okay, and these interleukins will tell the bone marrow to make more white blood cells. Now with leukophoresis, we didn't have one clear pathway like erythropoiesis. We had two pathways. Does anybody remember those two pathways?
Intrinsic.
That's hemostasis.
Lymphoid stem cells and myeloid stem cells.
Right, you have lymphoid stem cells and myeloid stem cells. These lymphoid stem cells give rise to your lymphocytes. They make it pretty easy, it's right in the name. The myeloid stem cells give rise to all other types. I think this is good enough for leukocytes. Anybody know something that I haven't covered that you want to cover? Okay, we'll move on to thrombocytes then. Anatomically, what are thrombocytes really? They're platelets, but what are platelets? They're just little fragments of cells. Actually, when we talk about the formation of platelets, you should know that they all stem from these large megakaryocytes, which stick little pieces of themselves into the bloodstream, and those pieces contain granules and all that good stuff, and it breaks off and flows into the bloodstream. This is really what a platelet is. Fragments of cells. Megakaryocytes. K-A-R-Y. These words are all in the thing. That's fine. We're really more worried about the function of megakaryocytes and what they do. Okay, this function, like you said before, was hemostasis, and we actually have 3 steps in hemostasis. All right, what are those 3 steps?
Vessel constriction, the
Vascular spasm,
Yeah.
which is really what you just said, blood vessel constriction. So as soon as you get a tear in your blood vessel, the blood vessel triggers to constrict to reduce the amount of blood you're losing. Number 2?
platelet plug formation.
Right. Platelet plug formation. And what you should really know about this is what kind of feedback loop is this?
Positive.
It's a positive feedback loop. We talked about 2 feedback loops, 1 positive, 1 negative in this chapter. Okay, again, during platelet plug formation, you have platelets sticking to this open, broken blood vessel, releasing chemicals to recruit more platelets, which release more chemicals, and this positive feedback loop feeds into itself until eventually you have so many platelets that it plugs the hole. Okay. And then number 3.
Coagulation.
Coagulation. Now, coagulation has 3 steps in itself. All right, 1, 2, 3. And really, coagulation is just a series of enzymes which activate other enzymes, until you get to the very end where you're converting something that's soluble in plasma to something that's insoluble in plasma. Okay, so something that's dissolved in the plasma to something that forms like a mesh, like a fibrous mesh that things can't get through. Okay, so what are these 3 steps?
Prothrombin activator.
Prothrombin activator formed. This can happen by 2 pathways,
Intrinsic or extrinsic?
right? And what is the difference here, really? Which one's faster? Extrinsic. Why? Well, yeah, you have a tissue factor here that's not present in the intrinsic. I'm just going to put TS for tissue factor. You have a tissue factor here that basically allows you to skip steps in the intrinsic pathway. Okay, so again, intrinsic, everything's contained in the blood itself, so you could coagulate blood with everything in the blood, but it's going to be slow, and that's for good reason. You don't want to coagulate anywhere. Extrinsic, if the damage is so severe that you have the incorporation of a tissue factor, now you speed the process up, right? That makes sense. If I damage not just the blood vessel, but also tissues, now I'll speed that process up and go. In fact, whenever you have blood vessel damage that's so severe, you're really using both pathways. So that's that, right? This step 2 of coagulation is,
Prothrombin is turned into thrombin.
right. Prothrombin is converted to its active form, thrombin. And then step 3.
Fibrinogen is turned into fibrin,
Exactly.
and then it creates the mesh.
Yeah, so what's really fibrinogen is going to be your soluble protein. Fibrin is insoluble. So upon converting your fibrinogen into fibrin, now you are going from this soluble protein, which is basically invisible, dissolved in plasma, to one that's creating this mesh, this net that starts to catch red blood cells and other formed elements. So that's good. And then the last thing we talked about is actually repairing the blood vessel itself, right? 3 steps in repairing the blood vessel itself. All right, the first step is what?
To pull the clot back?
Yeah, clot retraction. This is where the ends of the clot are pulling themselves together so that blood vessel wall isn't just a clot anymore, it's actually getting pulled back together.
What are we steps for? Sorry.
What?
What are we steps for?
Oh, this is just after hemostasis, right? What happens after hemostasis? You have 3 steps. Clot retraction, B,
Clot repair?
clot repair. You have 2 factors here which are encouraging the regrowth of 2 different parts of your blood vessel. Does anybody remember the 2?
Platelet-derived growth factor,
PDGF.
V,
This is
E.
going to repair your endothelial lining. And then
VEGF,
vascular endothelial
thelial,
growth factor. Okay, this is going to repair
the vascular wall.
vascular wall. Okay, and then finally, after we've pulled the wall back together, we've repaired it so it's new wall. What do?
Get rid of the clot.
Right? Dissolve the clot using plasminogen. Plasminogen is converted to plasmin, and this breaks down the clot. Okay, so we went through this entire chapter in about 45 minutes. That's not too fast. But you can see that as you walk through this, there are things that you remember or things that you've reinforced in your head and things that maybe you don't. Again, this is showing you sort of where you need to focus as you go through each chapter, and that's going to help you study. Okay, so
Professor McLean, what is C?
C is converting plasminogen into plasmin, right? This plasminogen is inactive. The plasmin is actually breaking down fibrin, right? breaks down the quad. Okay, let's continue on. Let's see how far into chapter 18 we get. This is probably the more difficult chapter. Would you say that's
Endothelial
accurate?
lining.
Yes.
Endothelial lining.
But it doesn't have to be the more difficult chapter. Again, when we're going through chapter 18, we can treat it just like chapter 17. You want to tell the story, and in order to tell a story, you need to know the anatomy, the function, and then how they're related, right? How does the anatomy do the function? How does the function relate to the anatomy? Okay, so let's start with chapter 18. The best way to start with chapter 18 is to talk about blood flow through the heart. Okay, this is something we talked about before. I'm going to draw my best part.
Same thing, worse.
And the valves here. Out. This guy here. And with a valve. And then this guy back here. With the valve. Okay, so blood flow through the heart. Okay. Let's just go ahead and start with the systemic circulation because this is where it's easiest to start. The systemic circulation is delivering blood. What kind of blood to the heart? Oxygenated.
Deoxygenated
Deoxygenated blood. And where does it go?
to the right atrium.
Okay, the right atrium. Now, before crossing into the left atrium, right ventricle, what valve must it go through?
Tricuspid.
Yeah, so you're gonna need to know tricuspid here. Yes.
I have a question. And maybe I'm just confused. I thought the right atrium receives, that's the pulmonary system. The systemic was on the left side.
The right ventricle is pumping towards the pulmonary system. The left ventricle pumps out into the aorta. The right atrium is receiving deoxygenated blood from the systemic circuit. The left atrium is going to receive oxygenated blood from the pulmonary circuit. So this is why we're going through it. Okay. All right, so right atrium receives deoxygenated blood from the systemic circuit, and then passes through this tricuspid valve into
The right
the right
ventricle.
ventricle. Now we're pumping it out through this valve,
Pulmonary semilunar valve.
pulmonary semilunar valve. Okay, from there it goes to the
Yep.
pulmonary circuit. And does what?
Picks up oxygen.
Picks up oxygen. So now I have oxygenated blood returning where?
To the pulmonary veins.
I'm sorry, the book says, the left side of the heart receives the oxygenated blood returning from the lungs and pumps this blood throughout the body to supply oxygen and nutrients to the body. The blood vessels that carry blood to and from all body tissues form the systemic circuit. So I'm confused, I'm losing.
Well, you just said the left atrium receives oxygenated blood from the pulmonary circuit, and this is where we were. Okay.
But you have systemic. on
I think she's
that side.
confused because it's the patient's right, not your right.
That's what it means.
Oh.
Yeah, it's the patient's right side,
No, no,
not
no.
your right
I mean,
side. So
it's the
she's
right.
backwards?
The right's the right, the left's the left, right? This is
But
the
right-
patient.
It says the right side.
She's
is the
confused about
pulmonary
this side.
circuit.
The right ventricle pumps into the pulmonary circuit. That's correct. But the right atrium is the receiving chamber. It's receiving from the systemic. You're not going to receive blood from the same circuit that you're
Right,
pumping
right.
to. That makes
I
sense.
think it's because it's not your right, it's the patient's right, so it's really left. Right, so you're looking.
I'm just saying,
I
as
think she has a
student,
backwards, she's looking at it backwards.
I think if you wrote pulmonary on the right side, because the tricuspid side is the right side, that's the pulmonary systemic, pulmonary, circuit. And the left side is the systemic, circuit. I mean, that's in all the books that I'm reading.
Yeah, well, technically, both sides are pulmonary and systemic, because, again, your atrium are gonna be receiving from one circuit. My right atrium receives from my systemic circuit, my left atrium receives from my pulmonary circuit. My ventricles are gonna pump into the different circuit. So my left ventricle is pumping into my systemic circuit, my right ventricle is pumping into my pulmonary circuit. So the receiving chambers and the pumping chambers are obviously gonna push this blood into and receive blood from different areas, right? So it really doesn't matter, I mean, I could write it down here, but as long as I draw an arrow to the right atrium, this is where the systemic circuit blood is going, right? After I dump off all my oxygen, it goes back to the heart, to the right atrium. That makes sense?
I'm just saying, if you give me that on the test, I'm gonna be. just
Okay,
don't
well,
mark
luckily
it
there's
wrong.
no pictures on the test.
No, I'm not saying that, I'm just going by
telling you what it
said.
is.
Left side is pulmonary,
The
left
left-
side is systemic, right side is pulmonary. I just hope before we get to anything like that, you understand, I understand the process, it's the wording I'm getting confused, but keep moving, keep
Okay.
moving.
The only other thing I can say is that it's a circuit, so it's all connected.
I know
Meaning
it's
the right ventricle, although it does pump into the pulmonary circuit, it's receiving blood from the systemic circuit. Okay, so you know, if we were to write this out,
You should know confused.
systemic,
I'm gonna be so
right
lost.
atrium, right ventricle, pulmonary, left atrium, left ventricle, and then back to the systemic. Okay, so
That makes
you know, this is, you know, part of the systemic too. Just because it's, you know, it says right side pulmonary, it's receiving systemic circuit blood. Okay, the left atrium is receiving pulmonary blood, even though it's, I don't know why they would call it part of the systemic circuit, because it's all one circuit. I think the book describes it this way as well.
All right.
Alright, so continuing on. The systemic circuit is pumping blood into the right atrium. And not pumping, but dumping blood into the right atrium. It goes through the tricuspid valve into the right ventricle, out through the pulmonary semilunar valve to the pulmonary circuit where it gets oxygenated, returns back to the left atrium, and now travels through what valve?
The metrial,
Through the bicuspid valve,
it's the same thing.
into the left ventricle,
But I think that's the one that he's
and then
gonna
out
like put in.
Aortic semilunar
the
valve.
aortic semilunar valve, and then it goes back to the systemic circuit. Okay, so this is good for mastering the anatomy of the heart because you have all the chambers and all the valves down. That's not really the only thing we talked about. We also talked about the heart layers. We have a few heart layers here: pericardium, myocardium,
Endocardium.
and endocardium. Okay. Now the pericardium does what, or consists of what? So we have an outer pericardium, which is the fibrous pericardium. The fibrous pericardium is really there to do what? Anchor and protect, right? It's sort of like your fibrous outer shell to the heart. Okay, then we have an inner pericardium,
Serous.
the serous pericardium. And it forms sort of like a little sac around the heart, right? There's two layers of the serous pericardium. There's the visceral layer and the parietal layer. The parietal layer is right under the fibrous pericardium. The visceral layer, also known as the epicardium, is right above the myocardium. In between these two layers is what?
Fluid.
Is fluid, right? Serous fluid. And that fluid is really there to make sure that as the heart's beating, because the heart does beat, the heart's moving, that it's sort of kept in a friction, I wouldn't say frictionless, but less friction environment, right? There's less friction here because it's surrounded by this serous pericardium filled with fluid. Okay. The myocardium, what does
Heart
it do?
muscle.
Yeah, this is the thick muscle layer. it's responsible for the contraction. Not only do we find muscle here, but we also find connective tissue in the cardiac skeleton. Okay, and then the endocardium. What does it do?
Lines the inside of the heart.
Yeah, it lines the inside as sort of a slip and slide. So that blood doesn't have to go up against this rough muscle, but it sort of has a nice, smooth endocardium lining to flow against, right? It's smooth and flows.
When you got myocardium, muscle what?
Muscle, so it can contract, right? Leads to contraction. And we also find the cardiac skeleton here. I know I'm going a little bit fast because we're running out of time here. I'd like to get to physiology a little bit. But this is really it for, this is the majority of the anatomy. I wouldn't say that's it. We also talked about the differences between semilunar valves and AV valves, okay? These are important differences because, again, the semilunar valves are protecting backflow from where to where.
The atrium.
No, the semilunar valves, again, from the great vessels
Back into
The ventricle.
back into the ventricles. The AV valves are there to protect backflow from the ventricle to the arteries, atrium. So the AV valves are experiencing a lot of pressure. Why? Because they're stopping backflow of these ventricles. These ventricles, which are really the pumping chambers of the heart, the strong muscle, thick muscle there, which are causing a lot of pressure. So really, these AV valves have two sort of differences from your semilunar valves. They have the papillary muscles, and they have these chordae tendineae, which attach them to the papillary muscles, right? Remember, these are the heartstrings which hold down the AV valves when they close shut. Okay, so that's important too. But slip and slide. All right. So continuing on to the physiology. So
I guess it looks like the second
does anybody have any other questions? We have about 15 minutes left, and I would like to cover physiology. The physiology of the heart can be broken down into two parts: electrical activity and motor activity, right? The mechanical activity of the heart. These two parts are obviously related. Whenever I have electrical stimulation, it is then followed by mechanical contraction, but it's easier to break these things down into two separate parts. Okay. So let's look at electrical activity first. The electrical activity of the heart is designed to allow the heart to work as one full unit. Okay. In order to accomplish this, you need to know a little bit about the microscopic anatomy. Remember, in between heart cells, we have these intercalated discs with two cell junctions. What are those two cell junctions? Right, desmosomes and gap junctions. The desmosomes are going to link the cells how? Physically, right? The desmosomes are sort of like nails or spot welds where you're gluing these two cells together so that when one contracts, it's not just ripping off from the others, right? They're physically linked. How do the gap junctions link these cells? Exactly right. They're electrically coupling these cells so that when one cell goes off, all the cells that are connected to it through gap junctions also go off. Again, we don't have nervous innervation of cardiac muscles like we do skeletal muscles. We don't have a nerve which goes down and touches each cardiac cell and says, hey, go off. Instead, they're all connected through these gap junctions and desmosomes. Okay. So let's sort of draw this up. We're worried about two different types of cells here. Here's my cardiomyocyte. And again, connected via gap junctions, I have these very specialized cells known as pacemakers. The setup around these cells is the same. I have high amounts of what on the outside?
Calcium
Calcium,
and sodium.
sodium. And I have high amounts of what on the inside?
Potassium.
Even though the setup is the same for these guys, they have different proteins, which create different action potentials. Okay, so you want to be able to follow each of these action potentials. One here for cardiomyocyte, and one here for the pacemaker. Okay, so what's the difference really? That's a good start, for sure. 1, 2, 3, 4 over here. No, that's not bad. 1, 2, 3 over here. So let's start with the 3 one. It's a little bit easier. All right, there's only 3 steps as opposed to 4. So step 1.
Repolarization.
Pacemaker potential. Right? We don't have a resting membrane potential. We have a pacemaker potential, and it looks sort of like this, right? A continuously depolarizing cell. And you want to know why that is? Well, we always have sodium entering these cells. We have these leaky channels, always allowing sodium to enter. If I have positive charges always entering, I'm always moving towards threshold. Once I hit threshold, what happens? Depolarization, right? This is caused by what entering the cell this time? Sodium still entering the cell, but what else?
Calcium.
Calcium is now also entering the cell as well. And then step 3. Repolarization. Okay. And that's caused by what? Potassium leaving the cell. Positive charge is leaving, I get more negative. Okay, back to this guy. 4 steps this time. Resting membrane potential is the first one, I'll give you that. But what happens once we reach threshold? Okay, so this just happened, right? Step 1, sodium's always entering the cell. Step 2, now I have a huge influx of calcium into the cell. Okay, this calcium is not just going to enter the cell, but it's going to spread in here and move us more towards threshold. Once we hit threshold in the cardiomyocyte, what happens? You get depolarization, right? This time caused by what entering the cell? Sodium. This is step 2 here. And then we have step 3, which is what? This is important. This is really the big difference between skeletal muscle and cardiac muscle. Step 3, we have this big plateau phase. And the plateau phase is caused by what? Yeah, exactly. We have calcium entering the cell at the same time our potassium's leaving the cell. Okay, my 2 positive charges here are going to negate the potassium that's leaving, and so we end up with this plateau phase, right? This phase where we're stuck, depolarized. Okay, and then for course repolarization. Come back down.
Is step 2 here, I'm sorry, Professor, is that depolarization?
Yes.
And the plateau phase, the sodium moves or enters the cell? The plateau phase?
The calcium's entering the cell at the same time the potassium's leaving the cell. All right, so we went through that pretty smoothly, and I hope you can do again, I'm showing you sort of how to practice this stuff at home. And the best way to do this is remove your notes and see how far you can get. I know it's awkward or uncomfortable or sometimes just not fun. But if you can start at least with some of this stuff and make your way to something else, wherever you stop, wherever you get stuck, you know you can go back to your notes and say, hey, I need to study this because this is what I don't know. Right? This is really going to help you out, I promise. So this is really good for electrical activity of the heart. One last thing we talked about with electrical activity of the heart is the series of excitation, right? This excitation goes through a series of structures through the heart to ensure that the heart is working properly. So you're going to have, yes.
For this step here, where we're talking the cardiac, contraction, is that -70 millivolts right there?
Yeah, that's just something I use there.
What number is? Okay.
0.
0.
This is just really negative and positive. Okay. So again, on the exam, you'll definitely have 2-3 questions about the different structures involved in the series of excitation, right? We're going over these concepts not because I think it's cool to do, but because you're going to have questions about it, right? So you'll have questions about this stuff too. So the first structure we talked about. The main pacemaker. Sinoatrial node, right? Exactly. Sinoatrial node. What about the sinoatrial node is? It's the fastest, so it's your main pacemaker. And impulses from the sinoatrial node go 2 places. What are these 2 places? Depolarize the atria. And to our next structure, our AV node, our atrioventricular node. Exactly, all right? So the atrioventricular node is really known for 2 things. First, it's your backup pacemaker. And secondly, delays signal. Again, this delay is so that the atria can depolarize before we shoot this signal down to the ventricle. So what's shooting it down to the ventricles? What's the only connection between the atria and the ventricles?
The valves?
Electrically.
That, septum, the septum?
Right, it travels down the interventricular septum. What's the name? AV bundle.
For junkies?
Known as the bundle of Hicks. And there's 2 things you should know about it as well. Again, it's the only connection point. From the atria to the ventricles, and this is talking about electrical connection, right? Not physical connection, but electrical connection. And it speeds up this signal. Again, why do we want to speed up the signal? Why would we want to shoot the signal to the bottom of the heart? Right, you want to contract from the bottom up, not from the top down, right? Bottom up is going to squeeze blood towards the great vessels and therefore out of the heart. Bottom down is going to not do that. It's going to actually cause problems. So it speeds up signal to shoot it down to the bottom of the heart. And obviously, the signal needs to go to both sides. So we have these two structures next, which carry it to both sides. What are those? Right bundle branch and your left bundle branch. Once in these two sides, now we have these tiny little fibers which actually extend up into the myocardium, and these are your Purkinje fibers. So, these carry to either side, extend into myocardium. Okay. We have 5 minutes left, so I'm going to stop there. But basically, you can see what we're doing, right? What we're doing is building a story. Okay? You want to start with the anatomy, and then talk about how the anatomy does the function. Okay? Does anybody have any questions about this stuff? I realize we didn't get to finish, but that's okay. I didn't plan on finishing. But if you want to review a little bit more, we can review in between this class and lab class. Okay, so we'll say, from what's 10:30.